Hello dear students, I'm Meghamala, working as Assistant Professor from EC Department, Institute of Aeronautical Engineering. And today, my topic is about design flow of ASICs and FPGA based system part 2. So already we have discussed part 1. In the part 1, we have discussed about what are the ASICs and what is FPGA. Okay, in this part 2, we will discuss more about what are the things involved in this particular topic. Okay, so coming to the objective of this ASICs and FPGA, mainly this course provides the students the knowledge about physical design flow. Basically, this we are in the last module. So this last module will help us to know more about the physical designing of a particular chip or else a module. Okay, it more consists of the physical design flow and logic synthesis for planning, placement, and routing. So in the design flow, so this is the last module in this particular subject. We digital design through Verilog. So in this last module, we are knowing about the design flow of a particular module or a chip. So in all this, what we can observe is we will be able to know how to design a module or else how to design a chip, and also the logic synthesis, the behavior or else the particular module behavior of a particular module or else a chip, that whatever we have designed, and as well for planning, the placing and the planning of a particular chip or else components to be planned in a particular area. And as well the placement and routing, which place, these are the major things that we can observe in this particular ASICs and FPGA, design flow of ASICs and FPGA. And experimental explore complete digital design flow of programmable ASICs through VLSI EDA tools. And after completing all this design flow, the later on we will able to know that the digital design flow programmable ASICs through VLSI EDA tools. So with the help of the EDA tools, after designing and floor planning, routing, and all these things, with the help of the EDA tools, VLSI EDA tools, we can able to perform the executing of the particular module or a chip. And then students work from design entry using Verilog code to GDSI file generation of an ASIC. So soon after performing everything with the help of the EDA tools, the students work from design entry using Verilog code to GDSI file. So after completing everything, after routing, after placing the design flow, first part is all about the design flow, and the second part is all about the dumping of using the EDA tools. We can able to go for the backend process. Okay, so after the backend process, what we will able to know is we will come to a proper structure. Okay, after using this Verilog code to a GDS file generation of the ASICs. And then we will see the map. So here this map talks about the hierarchy of the design, ASICs and FPGA design flow. So basically in this map, first thing is ASIC design. So this ASIC design, it deals with types and constructions. So it deals basically with what are the types of ASICs and the construction of that particular modules or a chip. So types and construction, where these types and constructions, they are considered for design flow, types of ASICs, and semi-custom ASICs, programmable ASICs, programmable technology, and ASICs construction. Okay, so this design, it deals with the types and constructions, where these types and constructions are mainly considered based on the ASICs construction, designing, types, semi-structures or semi-custom ASICs, programmable technology, and ASICs construction. Okay, and then ASIC design, it consists of system partitioning. Okay, first one, it consists of types and construction. The second one is system partitioning. So system partitioning includes measurement of partitioning. Okay, the partition of a system, it includes measurement of a partitioning. Okay, it includes the measurements of a partitioning, constructive partitioning, measuring partitioning, and then goes with the construction partitioning, iterative partitioning, and kernel link algorithm, some algorithm that we are able to use, and FPGA partitioning and power dissipation. So the system partition, the second part which consists the ASIC design, is the second part, that is system partitioning, where in this partitioning we can see the different types of segregation, okay, segregation of different categories. So we could see mostly the measurement of the partitioning of system, and then iterative partitioning and constructive partitioning, and as well some algorithm which is able to construct the things, and also FPGA partitioning and power dissipation. And later, the third point, the ASIC design, it consists of floor planning and placement. Okay, so after floor planning, in the designing part, floor planning and placement plays a vital role. So this floor planning and placement, it includes floor planning measurements. So in order to place some peripheral, in order to place some designs at a particular area, first thing we have to know the particular measurements. Okay, the particular area measurements we could able to know. Then floor planning measurements. After that, input output, power and clock planning. Okay, whatever the power that you are giving and clock generation, if it is a memory element, then obviously we have to give a clock, right? So I input and output, power and clock planning, and then measurement of placement, what sort of place that you are considering and the measurement of that particular place, and then placement algorithms and eigenvalue placements, and then iterative placements programming, okay, or else algorithm, iterative programming algorithm or iterative placement algorithm. So in this floor planning and placement, it includes all these criteria. Okay, so we have to achieve all these criteria in order to develop a particular module. Okay, so these things we will see only in the designing flow. Okay, only in the back end of the process. Then routing and circuit extraction. So in this routing and circuit extraction, this is a fourth part under the ASIC designing, and where the routing and circuit extraction, it includes global routing measurement, global routing, detailed routing measurement, and detailed routing algorithm, circuit extraction, layout, design rules. So this is about routing and extraction, exaggeration of a particular module, the circuit. Exaggeration of circuit, it includes routing, global routing measurements all over to all the corners, from all the around all the corners of the design, or else around all the corners of a chip. So global routing measurements in routing, okay, and then detailed routing. So to which and which, if you are considering 10 peripheral devices, so you have to know what are the devices are connected together. Okay, peer-to-peer communication sometimes we can see, and some of the times we can see from one device, one can be connected to device 10, like that. So detailed routing measurements and detailed routing algorithms itself, and also circuit extraction and layout designs. Okay, so these comes under the routing and circuit extraction. And then ASIC design, it's done with digital circuits using EDA tools. So after this 4 parts, so it's divided into 1, 2, 3, 4, 5. So the design of the ASICs have been divided into 5 categories. In this 5, we have completed 4 until routing and circuit extraction. After that, we are moving on to the usage of the EDA, VLSI EDA tools. So here, these digital circuits using EDA tools consist of, or else it includes digital design flow. One thing is basically digital design flow, and the second one is design and simulation. After designing the circuit, we have to run it, isn't it? We have to run it. Why? Because we should know whether the program is correctly modeled or not. Or we can able to know what are the errors that we are arising, or that the errors are occurring. So definitely we have to go through this simulation, design and simulation. And then synthesis and analysis. So after sorting out the problems, then we have to know what sort of solutions that we can give in order to omit the problem, the arised problem. So we have to go for this analysis and as well as the synthesis. And then floor planning and placement. So after getting to know the solution, then goes with the floor planning and the routing. So after routing, what we do is we will just route, or else we will interconnect all the peripheral device inside the module, and we place the devices, and then we interconnect the devices, we form a network. Okay, after that what we do is the routing and circuit extraction and the optimization of that particular module is being considered. So extraction, circuit extraction and optimization takes place, and then finally GDS2 file generation we will be observed. Okay, so after doing all these things, after completing all these 5 levels, finally we will get a particular or else a proper file, where that file contains all the outputs or else all the designed thing will be consisting in that file. From starting to the ending, all the process can be considered in this GDS file to generation. So this is just like hierarchical structures of how to design a ASIC designing or else FPGA designing. So ASIC design, it goes with 5 steps. Okay, it goes with 5 steps, where that it deals with the ASIC types and construction, which is first category or its first step is types and construction, and then goes with the system partitioning. What are the types? Okay, for example, being a designer, I must know there are many levels or there are many types of constructing a module. Okay, so I must know which one is the easier one, which one is a long-lasting one, and which one is a reliable one. So being a designer, I must be aware of all the things. So I need to take an active part in choosing the things, right? So after constructing the type and constructions, what sort of designing is it? And how can I construct, the easy way to construct? So all this can be done by using the step 1. And then immediately I should say I should look for the partitioning of the system. So if it is a complex designing, the partition can goes the partition can goes more than 3 times or 4 times. So overall I have to partition the system. Why we are going for partitioning is the partitioning will help us to connect the routing, and placement can be done easily without any obligations. Okay, without any obligations or without any messing up, we can easily make out the things possible. So I have to go for the system partitioning, which is a level 2. And then this system partitioning includes the measurements of that floor planning, measurements of the particular peripheral device that you are considering. And in order to done this, I have to go with the algorithm. Okay, what sort of algorithm will help me to incorporate in order to get a proper output. So all these things I have to aware, and this all will done in the second step, that is system partitioning. And then I have to move forward, where I have to go with the floor planning and placement. So floor planning and placement is it plays a crucial role in the designing part, where I have to place it and I have to route it. That means what? I have to place all the devices, all the individual devices particularly, along with the measurements, and obviously soon after placing I have to route it them. That means what? I have to connect it with them. The connection part, the interconnections should be made between the peripheral devices as well. Okay, and then in this floor planning and placement, I have to ponder on different algorithms, and I have to ponder on the measurements that I am considering about the different devices that I am considering, and also the different algorithms, and as well the clock planning, power and input output devices pertaining to that particular particular module. And then coming up with the soon after the third, that is placement and floor planning and placement, I have to move forward, where I have to route now and then extract the circuit. So in the routing and circuit extraction, I have to look after the measurements of particular things. Okay, mainly global routing. If my if my partitioning of a circuit is globally, means I have to look after the globally routing. And if it is if my circuit partitioning is only meant for some part, then I have to route it to some particular part or to some particular space. And then circuit extraction. Okay, and then after finally layout design rules, I have to concentrate on layout designing rules. Okay, and in the layout designing rules, I have to consider about the thickness of the material, about the thickness of the particular devices, and as well about the materials that I am using. Okay, and all these things will be considered. And soon after routing and circuit extraction, the final thing is I have to test. So for this test, I need some tools. Okay, so EDA tools are going to help us, or else EDA tools will make us to know the particular errors, or else they will make us to feel comfortable in order to obtain a particular structure of a module. Okay, so in this I have to analyze the things, I have to synthesize the things, simulation can be done, floor planning, routing, placement, and all this will be done. Finally, I have to, after getting the clear structure, clear picture of a particular module, then I have to save it in a file, GDS to file generation. So this is very particular, this is a very important to understand and a very important topic to remember, how the designing flow of ASICs takes place. Okay, and then we'll move forward. So here the integrated circuit basically it consists of the wafer lot, die, and the mask layers. So here wafer, what is a wafer? In order to construct each and every circuit, the circuit has to the circuit consists of many things, right? Many semiconductor devices. With the help of semiconductor devices, insulators, then only with the help of all these things we can able to construct a proper structure or as a circuit, right? So the wafer plays a vital role, where it is a circular piece of a pure silicon. It is a circular piece of pure silicon, 10 to 15 centimeters in diameter. Wafers of 30 centimeters diameters are expected soon. So usually we are in order to construct some wafer, we are using the diameter of 10 to 15. But in the coming generation, we could say the 30 centimeters of diameter can be expected. And then wafer lot is nothing but 5 to 30 wafers, each containing hundreds of chips dies. So wafer lot, this is a wafer lot, where this wafer lot consists of consists of hundreds of chips. So this wafer consists of hundreds of chips. Okay, and then depending upon the size of the die. So based on the die, this particular wafer, okay, based on the die, the particular wafer consists of hundreds of chips which are incorporated onto it. Okay, and then coming to the die. What is this die? A rectangular piece of silicon that contains one IC design. So this is a die. So this contains of silicon. This is silicon chip. This is silicon chip where it contains one IC design. So this is an IC where this IC consists of the wafers, and in wafers we can see the hundreds of chips which are incorporated onto it. Okay, so these are interrelated to each other: die, wafer lot, and as well wafer. And then coming to the mask layers. So what are these mask layers? Each IC, each integrated circuits manufactured with successive mask layers, 10 to 15 layers. So these mask layers consist of each IC. If I suppose this is IC2, IC1, IC3 like that. So here we can see 15 layers. So overall we are saying that this is a mask layer. So mask layer consists of a layer kind of thing where each IC, the layer, each IC is manufactured with successive mask layers. So these mask layers, it could be around 10 to 15 layers. And then the first half design or so layers define transistors. So here we will say that the first half design. Okay, so the first half design, half dozen, that is the first half dozen, the 30 layers are defined transistors, and the other half design define interconnect. So here in this mask layers, we see number of layers which are the number of layers are formed in order to form a particular mask layer. So this mask layers consist of a numerous number of layers inside it. So few layers are also half dozen layers meant for the IC or the transistors, to define the transistors, and half layers or half wafers are meant for the interconnection purpose. Okay, so all this we see, this sort of things we will be observing in the design flow of a particular IC or else a FPGA or ASIC. And then integrated circuit in a package pin. So this is a IC in a package pin, where this IC, we could see that some different kinds of IC, dual inline package IC, chip kind of IC, and now we see the pin grid array package. So this is a IC of pin grid array. So this is a pin grid array. All the pins, these are nothing but the pins. So all the pins on a particular grid are arranged serially. Okay, And this is a silicon die chip. So this is a silicon die. This is a silicon die chip. So the chip is under the package lid. So this chip is already has a package lid where it covers all the pins. So why this package lid is there means just in order to protect the pins not to get damaged easily. Okay, when you are transporting the chips or when you're transporting the ICs, there may be a chance of damaging, right? So in order to avoid that, what happens is this silicon die kind of chips will have a package lid over there, okay, just to protect it. So these are nothing but a package ICs. So ICs in a package kind of thing. So usually we have in the electronic circuits we have different ICs, IC 741, IC 555, like that. So these IC are very minute ICs where they have only 14 pins. Some ICs will have 8 pins. Okay, and some ICs will have three pins. So likewise, if some ICs, some integrated circuits will have more than 100 pins, right? So this could becomes under more than 100 pins. So we are calling this as a pin grid array, and as well as a silicon die or chips. And the evolution of IC. And now we will see how this IC come into existence or the evolvement of this particular IC. So basically we have in the ancient time we used this IC. The very first basic IC is in the 1962, that is called small scale integration. So small scale integration is a very first evolved IC. It consists of tens of transistors. Okay, it consists of tens of transistors and NAND and NOR gates as well. So this is a very basic kind of IC. In 1962, it came into existence and it consists of tens of transistors and NOR and NAND and NOR gates are incorporated with it. And then coming to the later on, after the days passed, after the years passed on, we have coming to another kind of IC got into evolution, that is in late in 1960s, that is medium scale integration. So this is MSI, medium scale integration. It consists of hundreds of transistors, where SSI, that is small scale integration, consists of only tens of transistors, only few transistors, whereas in medium scale integration consists of hundreds of transistors. And basically with the help of hundreds of transistors, we could able to design the counters. Okay, we could able to design the counters, different types of counters, up counter, down counter, ring counter, okay, ring counter, Johnson counter, and all these counters we can able to they come into existence only with the help of this medium scale integration, where it consists of hundreds of transistors. A much better we can see here. And then coming to the large scale integration. So in the mids of 1970, this large scale integration circuits have come into existence, and this consists of tens of thousands of transistors. So tens of thousands of transistors it consists. And then first microprocessor was introduced in this with the help of this tens of thousands of transistors, and that is in mids of 1970, where we call it as large scale integration. So from this era onwards, the evolution of the chip got increased. Okay, evolution of the ICs, integrated circuits, got into a proper evaluation. It got exploded more in from this mid 1970. And then after large scale integration, in 1980s, okay, in 1980s, the ICs got evolved into very large scale integration. So very large scale integration, it consists of started hundreds of thousands of transistors. So here only tens of transistors, but whereas here in VLSI, very large scale integration, we see hundreds of thousands of transistors. So hundreds of thousands of transistors, several billion transistors in 2009. So in 2009 till 2000, like with the if we are the earliest of 2009, we could able to construct, or else we could able to get out different types of chips or else devices based on hundreds of thousands of transistors. So for example, I can say here that 64-bit microprocessors have come into existence with cache memory, and floating point arithmetic unit. So all this have comes into existence in midst of 1980s, and that was with the help of VLSI, very large scale integration circuits, where here we are using this VLSI started the transistor, or it's a pin configuration, or it's a chip configuration of this is hundreds of thousands of transistors. With the help of hundreds of thousands of transistors, different kinds of digital circuits have been come into existence. And then finally, ultra large scale integration. So in late 1980s, this large scale integration have come into existence, where these integration circuits consist of more than about 1 million circuit elements on a single chip. So on a single chip, we can say 1 million. Okay, 1 million circuit elements can be accommodated on this particular single chip, and so we are calling it as ultra linear scale in ultra large scale integration. And for example, the Intel 486 and Pentium microprocessors use ULSI technology. So as this contains of billions of transistors over a single chip. So the different types of or the applications that we come across here is Intel 486 and Pentium microprocessors, where they use the ultra large scale integration. So this is just a gist of how the integration circuits got evolved in all throughout these years. Okay, from 1960 onwards to 2009, and still we are coming into different. The technology has been growing more rapidly. Okay, many new things have been seen in the electronical era. So this is all about just the evolution of integrated circuits. And now we'll see the technologies. So after evolution of this integrated circuits, the technologies which have come across based on this ICs are, first one is bipolar technology, where it is more accuracy. The accuracy is more for this bipolar transistors. Okay, and then MOS transistors. MOS is metal oxide semiconductor transistors, and these transistors they use the gate aluminum, and the low power consumption is low, and they are low cost. So these are the advantages and the evolutions of the different technologies in the integrated circuits. Bipolar junction are more accuracy that we have used, and then going to with MOS semiconductors, metal oxide semiconductors as a take the very less power consumption and the low cost, and also they use the gate aluminum. And then the complex metal oxide semiconductor, CMOS technology plays a vital role in this electronic era, where it has the gate polysilicon. It uses a gate polysilicon, and here as well, like MOS devices, MOS technology, even in the CMOS, they consider the low power consumption. Okay, low power consumption, and as well the cost is very less. And then finally, BiCMOS technology. Okay, bipolar complex metal oxide semiconductor technology. So in all these technologies, we could able to learn different types of the products that are evolved using this technology. And now coming to the types of ICs. So here in this IC, we have standard IC, ASIC and ASSP. So in the standard ICs are glue logic, the microelectronic system design that became a matter of defining the functions that can implement using standard ICs, and then implementing the remaining logic functions, sometimes called as glue logic, with one or more custom IC. So here, this particular sentence is talking about the glue logic. Glue logic is nothing but we know that using IC we can able to construct different sort of the circuits, right? Different circuits can be made or constructed with the help of a proper or normal ICs. But other than that, okay, implementing the remaining logic functions called glue logic with one or more custom IC. So, but with one single IC, we can able to perform the actions. But if you are using more custom ICs, integrated circuits, a glue logic can be implemented. It is nothing but the logic functions with the standard ICs. The functioning of the particular ICs can be make out with the help of this glue logic. Okay, why? Because this glue logic consists of different ICs which are accumulated on a single chip. And then coming to the ASIC and then ASSP, this application specific standard products. Okay, as application specific standard product. And here ASIC is application specific integrated circuits. So for different category of the designing part of a particular circuit, the different ICs, the different integrated circuits have been considered. So application specific integrated circuits. So for different types of applications, model designings, we will be using different integrated circuits based on the types and also based on the technology that we are using for the evolution of that particular IC. And then coming to ASIC and non-ASIC. So what is this application specific integrated circuit and non-application specific integrated circuit? So examples of ICs that are not ASICs include, these are the examples where they are not ASICs. That means what? They are purely ASIC. So they are purely ASIC. They include a part of memory chips such as sold as a commodity items, ROM, RAM, DRAM, SRAM, microprocessors. So these are nothing but the ASICs, examples of ASICs. And TTL, transistor logic, TTL equivalent ICs, and at small scale integration, medium scale integration, and large scale integration levels. So here we see the examples of ASICs include the transistor logic as well, or transistor logic equivalent ICs. So using transistor logic, with the help of ICs at different levels, we can able to construct. So with respect to small scale integration, with respect to medium scale integration as well, and also with respect to large scale integration levels as well. And then coming to the ICs that are ASIC include. Okay, so that are ASICs include. So a chip for a toy bed that talks. So these are the few applications where it includes the application specific integrated circuits. So these are the few examples: a chip for a toy that talks, and a chip for a satellite. Okay, and chip designed to handle the interfacing between memory and microprocessor for a workstation CPU. So here we can see the ASICs can be used as an interfacing devices. Okay, interfacing prominent. So where it interface between the memory and as well the microprocessor, and a chip containing a microprocessor as a cell together with other logic. So these are the few applications of application specific integrated circuits. And then now we will see the types of ASICs. So what are these types of application specific integrated circuits? So here we have full custom ASICs and semi-custom ASICs. So full custom ASICs have different categories, and semi-custom ASICs here also include different types. So under the semi-custom ASICs, we have standard cell-based ASICs, gate array ASICs, programmable ASICs. So coming to the programmable ASICs, we know that PLDs and FPGA. What is this PLD? Programmable logic devices, where it contains the lookup tables, conduct maps, and all sum of products and product of sums, min terms, and max terms of a particular device we can be easily observed with the help of the Boolean expressions as well. Whereas in one of the programmable ASICs is FPGA, field programmable gate arrays. Here in this gate arrays, we could, with the help of different gates which are connected in a different manner. Sometimes the gates will be connected parallelly, sometimes the gates are connected serially, but the mechanism can be, or as the execution of that, all the gates can be observed concurrently. The concurrently execution of the gates can be observed clearly. And also here, in order to know the errors, we have to go with the different mechanisms in order to sort out the errors: observability, sustainability, availability, and all. So these comes under the programmable ASICs. So full custom ASICs, possibly all logic cells and all mask layers customized. So here in this full custom ASICs, we see the mask layers. We are already in the previous slides here we have discussed, right? So what are these mask layers? Mask layers are nothing but this contains of different layers, okay, or one over the other. The layers are placed one over the other, and each layer has the IC is manufactured with the successive mask layers. So in the IC is manufactured over the layers. So half of the layers can be considered for the half dozen layers are considered for the transistor to define the transistor, and half layers are considered only for the interconnection purpose. So here in this programmable FPGAs, we see for programmable FPGAs or else a full custom ASICs. In the full custom ASICs, we are saying that all logic cells and all mask layers are customized. Okay, so this full custom ASICs consist of all the mask layers and as well the logic cells. And then goes with the semi-custom ASICs. So this semi-custom ASICs consist of standard cell-based, gate array based ASICs. So basically what is this gate array based ASICs is all the gates are based on the gates, different types of gates. We could able to design a particular circuit, okay, based on the gate arrays. The array of different gates can be arranged in a proper manner, and the connecting, routing, placing and all can be given to it. With the help of EDA tools, we can able to model a particular circuit. And then finally programmable ASICs. So semi-custom ASICs. So semi-cusum ASICs consist of all logic cells are pre-designed. Okay, they are before itself pre-designed. Some possibly all mask layer customized. Here, mask layer customized with the help of pre-designed. Okay, all the designs, all the considerations with respect to the gates or else with respect to the different arrays of different gates. All these are pre-designed. So this is a bit differentiation between the full custom ASICs and the semi-custom ASICs. And coming to the full custom ASICs, it includes all customized logic cells. So here, full custom ASICs, it includes all customized logic cells and they have their mask layer customized. As I said they consist of mask layers. See, full custom design consists of mask layers, all logic cells and mask layers customized. So they have all their mask layers customized, and then manufacturing lead time is typically 8 weeks. So here the time taken in order to manufacture such kind of ICs is basically 8 weeks. So the time taken to make the IC, it does not include the design time. It only manufacturing, doesn't include the designing time. Designing time is nothing but the placing, routing, okay, algorithm performing, and what else? Algorithm performing, and all the 5 categories which we have seen in the concept map. It doesn't include that in this particular time. Okay, it takes only for manufacturing. Only for manufacturing lead time is it will take 8 weeks, but it excludes the IC. It excludes the design time. And then coming to the advantages, we have advantages, disadvantages, and some examples for this full custom ASICs. So advantages are it offers highest performance. Okay, compared to the semi-custom design, the full custom design, it offers the highest performance, and also it it has a low cost because smallest die size. The die size is very small. Because of the die size is small, obviously the cost goes to the low price. The price is very less. These are the advantages for full custom design of ASICs. And then coming to the disadvantages. So the disadvantages we have is increased design time. The design time is bit lengthy. Okay, the time taken in order to design some particular circuit is bit lengthy, and then it has some complexities in the designing purpose. Okay, in the designing part, we arise some complexities and higher design cost. So as it has a higher designing time, the time taken is more maximum, and as well as the cost is also maximum. Design cost is maximum and the higher risk. So in the full custom designing of ASICs, if you find any kind of damage between in the pins, okay, in the pins that you're considering, or in all the in any peripheral device, if you're finding any damage, any crack kind of thing, if you find in the ICs, what happens is that whole damage, the whole chaos will be occurred in that particular circuit. So we have to be very careful in order when you are choosing for the full custom or the semi-custom. And the examples goes microprocessors, high voltage automobile control chips, and analog and digital communication chips, sensors and actuators. So these are the full custom design ASICs. We know the microprocessors, right? We know the microprocessor, different types of microprocessors we come across, and then high automobile control chips, and as well sensors and actuators, where these are constructed, or else these are made with the help of full custom ASICs. And then semi-custom ASICs. So what is the semi-custom ASICs? Semi-custom ASICs consist of standard cell-based ASICs. So we call this semi-custom. semi-custom ASICs is standard cell-based ASICs. So, in shortcut, we can call as CBIC. CBIC. So, cell-based ASIC, right? So, CBIC is CBIC. Cell-based ASIC. So, CBIC. In shortcut, we call this semi-custom ASICs. So, use pre-designed logic cells, standard cell form. Even this will, the standard semi-custom designs, they use pre-designed, okay, pre-designed logic cells as well, where this pre-designed logic cells or cell standard cells comes, which can take from the libraries, standard cell libraries, and other mega cells, that is microcontrollers or microprocessors. These are called the mega cells. Why? Because all the peripheral devices are accumulated only in one single chip. So other mega cells and full custom blocks, okay, full custom blocks and system level macros, and then function standard blocks and cores, etc. So here this semi-custom ASICs are nothing but we can make use of the library, and we could see in the microprocessor and microcontrollers and system level macros, and then functional standard blocks and cores, etc. Then finally, we get all mask layers, customized transistors and interconnect. So here in the semiconductor semi-custom ASICs, we see all the mask layers customized. Okay, all these layers are properly customized, okay, properly meant, and then the transistors are interconnected. All the transistors on each layers are interconnected properly. And then manufacturer lead time is about 8 weeks. So here, in order to manufacture a particular product with the help of this semi-custom ASICs, it takes about 8 weeks, and then custom blocks can be embedded. So if you have any custom blocks are nothing but the custom blocks are with respect to the semi-custom ASICs, they can be embedded later. And then coming to the standard cell-based ASICs. So what is the CBIC in general? So this is about this is a figure where you see here routing a CBIC cell-based IC. How the routing takes place in a cell-based IC. So here we see low power pads. These are the low power pads. Row end cells. These are the cells, right? So these are the low end cells. These are the spacer cells. And here we see, like you can observe here, this is a feed. So the feed can, the power can be considered from this feed through. And so here we have cell 11, cell 14, 23, 132, and this is a metal, okay, metal 2, and these are the power cells, and this is a metal 2, okay. And you can see here rows of standard cells. These are the standard cells. These are the rows of standard cells. And so if you observe here, we could see here the routing, the placement and routing takes place. Okay. So this is what aux parallel of, it is of part of flexible block 1. So this is a minute block. If you observe this block is nothing but a minute block. This block is all about this. So each and every block consists of gates, okay, which are interconnected. So here you see the connection. No, here we don't see any connection. All the metal 1, metal 2, they both are connected together. And here, from here we can give the connection, okay. And here there is no connection, but here we have a connection, the power supply. So here the feed can be given through this part. And then here if you observe the same block, this is what for the explanation purpose he has given. So this is a standard cell area. And these are the fixed blocks 2, 3, 4, 5. These are the fixed blocks. Standard cell area. Each cell consists of each block consists of different microcells or macrocells. Okay, based on or constructed with respect to the gates. Okay, and if you are concerned about the full custom ASICs, these blocks are semi-custom ASICs. And then a wall of standard cell forms a flexible block. So this is standard cell. The wall of standard cell is nothing but the flexible block. This is a flexible block. So metal 2 may be used in a feed through cell to cross over rows that use metal 1 for wiring. So here you see metal 2 and metal 1. Metal 2 is for metal 2 is for feed through. So that means what the power supply can be given. So the power supply, that is the power can be accessed with the metal 2. And then metal 1 is nothing but it is for wiring. So metal 1 is meant for wiring. Okay, and then other wiring cells are spacer cells, row end cells, and power cells. So these are the different cells we could see in a particular standard cell area. So this is a standard cell area. So in the standard cell area, we have different blocks. Okay, so this particular cells, few cells are meant for the row end cells, and few cells are meant for the spacer cells, and few cells are meant for the power cells. Okay, and the connection of between two metals can be given with the help of feed through. Metal 1 is for wiring, and metal 2 is for feed through. Okay, the power can be given for metal 2. So this is a standard bell CBIC configuration that for the understanding purpose. And then the standard cell in a flexible block of CBIC is given as like standard cell in library is constructed using full custom design methodology. So here standard cells, this is a standard cell, right? So this standard cell, it is constructed with the help of full custom CBIC, full custom design methodology. And then same performance and flexibility but reduced time and risk. So why we are going for full custom is the performance is same. When you compare the full custom and semi-custom, we see in both the performance is same, but the risk is less in the full custom. So in order to reduce the time and risk, and then ASIC designer defines only placement of standard cells. So here, ASIC, being an ASIC designer, what I have to do is I have to concentrate more about the routing or the connecting of the standard cells. These are the standard cells, right? So here I have to define, also I have to concentrate more on the placing of the standard cells. Defines only the placing of the standard cell. So here you see this is one standard cell, this is another standard cell, another standard cell, one standard cell. So here the designer will define the standard cells, placement of the standard cells, and then it can be placed anywhere on the silicon. So this is a silicon chip, where in this silicon chip I can place the standard cells, okay, or as a layer wise. So each standard cells consist of metals, it consists of blocks, fixed blocks, okay, with different dimensions, measurements. And then flexible block in ASIC. What is this flexible block in ASIC? The CBIC, that is CBIC. So flexible block, it consists of the standard cells are designed like bricks in a wall. So here if you observe standard cells, so these are the standard cells. So the standard cells are considered as a bricks in a wall. So if you consider this is a room, you can see these are the bricks. So what are these? These are nothing but the standard cells. So standard cells are considered as a bricks in the wall. And then groups of standard cells fit horizontally to form rows. So here horizontally the standard cells are placed horizontally on a silicon chip. On a silicon chip the standard cells are made. So horizontally form a rows. The rows stack vertically to form flexible block reshaped during design. So the rows stack vertically to form flexible block. So horizontally we are placing the standard cells in the chip, whereas vertically you can see the design of that particular reshape during the design. The vertical we can reshape during the design. While you are designing, we can reshape it when the stack is vertically to form a flexible block. Then flexible block connected with other standard cell blocks or full custom block. So here flexible blocks can be connected with the other system blocks. Okay, other system blocks, or else see these are the walls of, this is nothing but the flexible blocks. The walls of system blocks is nothing but the flexible blocks. So here the flexible blocks connected to other standard cells or full custom block. So this can be connected to the other standard cells or the full custom block. So this is about a flexible block in CBIC. Flexible blocks are nothing but it acts as a wall. Okay, it acts as a wall to the it acts as a wall in the chip. See here, a wall of standard cell forms a flexible block. And then coming to the advantages of CBIC. So what are the advantages that we can find in this CBIC is they save time money, and reduce risk. So there are major advantages that we can see with the like when we use the CBIC is we can save time, money, and as well the reduction of the risk can be seen. And then standard cell optimize individually for speed or area. So in order to optimize the speed and area, okay, in order to incorporate, or else in order to reduce the area, or else in order to increase the area, we can say that the standard cell can be optimized individually. That means individual cells can be optimized in order to increase or decrease the speed or area. And then coming to the disadvantages as well. So this CBIC has a few disadvantages. Time to design standard cell library. So to design a library, it requires some more time, and the expenses of designing standard cell library, so it takes some the expenses would be maximum in order to design the standard cell library, and time needed to fabricate all layers of ASICs for new design. So here, in order to fabricate all the layers in the new design, it takes more time. Okay, so these are the few disadvantages of CBIC. So this is about the design of ASIC and FPGA, which is a basic designing system in the it's all about the part 2. So all these things will be seen at the back end of the process of the particular chip designing. Okay, so in order to design a particular chip, or else in order to design a particular circuits, then you have to go through all these standard things. Okay, you have to be aware of all the placing and routing, and you have to be aware of all the materials that you are using, the thickness that you are maintaining, and as well the connection that you are giving, and also the technology that you are making use of the technology. So what sort of IC that you are using, and what sort of technology that you are making use of, and all these things are considered in order to get a particular circuit. So this is a very important map, and you have to learn this map. You just concentrate on this map so that it can be easily understood. The concept can be easily understood. So this is all about the designing of ASICs and FPGA. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.